Today, we're going to be taking a closer look at combustion analysis reactions. These reactions in general involve hydrocarbons or organic molecules with oxygen. CXHY represents a general hydrocarbon where the subscripts X and Y can vary in number. This organic molecule is burned in the presence of oxygen, a diatomic molecule, as shown here by the subscript 2. The products of organic combustion always include carbon dioxide and water. Occasionally, there are other products including different elements. For example, in fireworks, different metallic compounds are used to produce unique colors as well as for the whistling and crackling effects. Let's take a look at a common combustion reaction that occurs when lighting a gas stove or seen in the lab when using a Bunsen burner. For this combustion reaction to begin, the activation energy for the reaction must be overcome. Often, combustion reactions begin with a burning match or another flame, which provides the heat needed to initiate the reaction. Here, methane gas, CH4, is ignited in the presence of oxygen gas to produce carbon dioxide and water. You can see the chemical change occur at the molecular level when looking at the reactants and products pictured here. Let's take a closer look at the molecular view. In any chemical reaction, the law of conservation of mass is observed. Matter is neither created nor destroyed in a chemical reaction. Our first reactant has 1 carbon, pictured here, and 4 hydrogens, pictured in white. You can see those same elements in the same quantities on the product side. Our second reactant, oxygen, is a diatomic molecule. You can see a total of 4 atoms, pictured in red, of oxygen on the reactant side, and the same number of oxygen atoms, pictured in red also, on the product side. So in a chemical reaction, the same number of atoms are present on both sides, but they're arranged in different chemical combinations. Now that we have an understanding of what a combustion reaction looks like, let's take a look at some calculations involved with organic combustion reactions. Example 1 gives us an unknown compound containing carbon, hydrogen, and oxygen. So these are the 3 elements in our unknown compound. We're given a 0.75490 gram sample of the compound that burns in oxygen to produce 1.9061 grams of carbon dioxide and water, 0.3370 grams of water. Let's take a moment to just write this chemical equation out. So we don't know this unknown compound, the exact formula of it, but we do know that it contains carbon, hydrogen, and oxygen. So we're going to put the variables X, Y, and Z in place of the subscripts that are going to belong to that formula. So this unknown compound reacts with oxygen gas, that's what the G stands for, to produce some amount of carbon dioxide, 1.9061 grams in this case, which is also in the form of a gas, plus water in the form of vapor. So that would be also as a gas. All right, now we're going to take a look at part A, calculate the individual masses of carbon, hydrogen, and oxygen in the original sample of 0.7549 grams. So we're going to start by solving for carbon, the first element listed here. If you examine the compounds, there's 2 compounds that contain carbon. One is the unknown compound, which we do not have the formula for, and the other one is carbon dioxide. We know the formula of carbon dioxide is CO2, and we're given the amount of carbon dioxide in grams. We're going to use the given value of carbon dioxide to determine the amount of carbon present in this reaction. Let's set up our dimensional analysis. Our first step will be to convert grams of carbon dioxide to moles of carbon dioxide. After adding the masses of carbon and oxygen in carbon dioxide together, we get 44.01 grams per mole as our molar mass for this formula. So let's plug that into our dimensional analysis setup. Let's cancel grams of carbon dioxide. Now we need to get rid of moles of carbon dioxide. Remember, we're trying to figure out the grams of carbon present in this compound. Our next step will be to set up a mole ratio of moles of carbon dioxide to moles of carbon. In 1 mole of carbon dioxide, we have 1 mole of carbon. Notice that there are no subscripts next to the carbon. That's how I know that there's 1 mole of carbon in 1 mole of carbon dioxide. Our setup allows us to cancel out moles of carbon dioxide. Now we're going to convert from moles of carbon to grams of carbon. Moles of carbon cancel, and now we multiply the top and divide by the bottom. Our answer comes out to 0.52016 grams of carbon. Our next step will be to determine the mass of hydrogen present in the original sample. So if you look at, again, our equation, you can see that we do have hydrogen present in the unknown compound. However, we don't know the formula of the unknown compound, so we can't use the mass of this compound yet. The other place you see hydrogen is in water. And in the problem, we are given the mass of water. So that's what we will use to determine the mass of hydrogen. Let's write down our given value. And now let's set up our dimensional analysis. Our first step is to convert from grams of water to moles of water. Remember, the molar mass of water is 18.02 grams per mole, and this is how you calculate it. Grams of water cancel. Now we're going to switch from moles of water to moles of hydrogen using the mole-to-mole ratio. 1 mole of water contains 2 moles of hydrogen, as shown in the subscript here. Moles of water cancel, and our final step will be to convert from moles of hydrogen to grams of hydrogen. One mole of hydrogen equals 1.01 grams of hydrogen. We're going to cancel out the moles of hydrogen and multiply the top and divide from the bottom. Our answer comes out to 0.03778 grams of hydrogen. Remember to round your answer to 4 significant digits because we're given 4 significant digits in water. The final step now is to determine the mass of oxygen present in the original compound. Once again, we do not have the formula of the original compound, so we don't know how many oxygens there are in that formula. Notice oxygen is also in another place on the reactant side. It's present all by itself in a diatomic molecule. And then on the product side, it appears in 2 places, in carbon dioxide and in water. Now, since we already have the mass of carbon and the mass of hydrogen present in the unknown compound, we can subtract the masses of carbon and hydrogen from the total mass of the unknown sample to determine the mass of oxygen. So let's set that up. The mass of oxygen equals the mass of oxygen can then be solved for by subtracting the combined mass of carbon and hydrogen that we just solved for from the mass of the unknown compound. Let's plug in our numbers. 0.75490 grams is the mass of the original sample, minus the masses of carbon and hydrogen combined. The answer comes out to 0.19696 grams of oxygen. And now we've completed part A. Let's take a look at part B. Our first step to determine the empirical formula will be to convert the masses that we solved for back to moles. Let's set up our dimensional analysis. Let's divide to convert to moles. For moles of carbon, we got 0.043311 moles of carbon. For moles of hydrogen, we got 0.03741. And for oxygen, 0.012310 moles. Remember, when solving for the empirical formula, once we convert from mass to moles, the next step is to divide by the lowest number of moles. Comparing moles of carbon, hydrogen, and oxygen, we can see that the moles of oxygen has the lowest number. We're going to divide the moles of carbon, hydrogen, and oxygen by the moles of oxygen. What we're doing here is determining the ratio of moles of carbon to moles of oxygen and moles of hydrogen to moles of oxygen. When we perform this first calculation, notice the answer comes out to 3.5184. The second value comes out to 3.039. And the third value is just 1. When we're evaluating the ratio, we need to be looking for fractions like 0.25, 0.5, 0.33. Upon looking at the numbers, you can see that oxygen is just simply 1. Hydrogen can be rounded to 3. But carbon will need to be multiplied to eliminate that 0.5. So we'll multiply by 2 to get rid of the fractional value or the decimal. 3.5 times 2 comes out to 7. Since we chose to multiply carbon by 2, we also need to treat the other elements the same way and double them as well. So 3 times 2 comes out to 6, and 1 times 2 is 2. These numbers give us the subscripts for our unknown compound. So our unknown compound is C7H6O2. And that's the empirical formula. In example 2, we are given a compound containing the elements carbon, hydrogen, nitrogen, and oxygen. When a 2.1106 gram sample is burned in excess oxygen, 3.2017 grams of carbon dioxide are formed. The combustion analysis also shows that the sample contains 0.1710 grams of hydrogen. An equation representing this combustion reaction can be written as follows. C, H, and O each have unknown subscripts, so we're using A, B, C, D to represent those unknown numbers, plus oxygen gas yields carbon dioxide and water as products. In part A, we're asked to determine the mass in grams of carbon in the original sample of 2.1106 grams. So because carbon is also present in carbon dioxide, we're going to use the mass of carbon dioxide to determine the amount of grams of carbon present in the original compound. Let's record our given value of carbon dioxide and set up our dimensional analysis. Now let's convert grams of carbon dioxide to moles of carbon dioxide. In 1 mole of carbon dioxide, we have 44.01 grams of carbon dioxide. Grams cancel. Our next step is to set up the mole ratio between moles of carbon dioxide and moles of carbon. In 1 mole of carbon dioxide, we have 1 mole of carbon. Moles of CO2 cancel. And now we convert moles of carbon to grams of carbon. One mole of carbon has 12.01 grams of carbon. Moles of carbon cancel. Let's use our calculators to solve. Your answer should come out to 0.87372 grams of carbon. Now let's take a look at part B. When the compound is analyzed for N content only, the mass percent of N, or nitrogen, is found to be 32.16%. Determine the mass in grams of nitrogen in the original 2.1106 gram sample of the compound. This is a percent problem. So all we need to do is take 32.16% and convert that to a decimal. Divide by 100, and that converts to a decimal, and multiply that by the mass of the original sample, which is 2.1106 grams. This will give us the mass of nitrogen. Upon solving, you should get 0.6788 grams of nitrogen. Part C asks for us to determine the mass in grams of oxygen in the original sample of the compound. Since we have the mass of hydrogen given to us here, and the mass of carbon that we solved for, and the mass of nitrogen that we just solved for, we should be able to add those numbers up and subtract them from the mass of the original compound to obtain the mass of oxygen. The mass of the original compound is 2.1106 grams. Let's plug in the masses of carbon, hydrogen, and nitrogen. Now let's add and subtract. The mass of oxygen should come out to 0.3871 grams of oxygen. In part D, we're going to determine the empirical formula of the compound. Remember, the first step in solving for the empirical formula is to take the mass values that we have for each element and convert to moles. Let's set up our dimensional analysis. Now let's go ahead and divide each of these setups. Now that we've converted from mass to moles, our next step when solving for the empirical formula is to divide each of the moles by the smallest number of moles present here. If you compare carbon, hydrogen, nitrogen, and oxygen, you will see that oxygen has the smallest number of moles. So we're going to divide all 4 of these by the number of moles of oxygen. Remember, in this step, we're comparing moles of carbon to moles of oxygen, and then moles of hydrogen to moles of oxygen, and then moles of nitrogen to moles of oxygen. So essentially, we're solving for the ratio. After examining the results of our division, you can see that for carbon, we can take the ratio and just round that to a 3. We can take 6.999 for hydrogen and round that to 7. And 2.003 can be rounded to 2. And then 1 just remains 1. These values here in pink will be the subscripts for our empirical formula. You don't have to write a 1 next to the O. It's just understood that when there's no subscript there, it means that there's 1 atom present. So this is the empirical formula. Part E gives us the molecular mass of the compound as 174.2 grams per mole. Using this data and the calculations we just performed, we're going to determine the molecular formula of this compound. So the first step will be to use the empirical formula that we just determined and figure out its molar mass. Let's start by separating out the elements and counting up the atoms. Next, we'll multiply each of these numbers by the molar mass of the element. Let's add our products. 87.12 represents the molar mass of the empirical formula. Because the molar masses of the molecular formula and the empirical formula differ, we know that they're not going to be the same formula. We need to determine the value of N to figure out what to multiply the empirical formula by to get the molecular formula. $174.2 grams per mole divided by 87.12 grams per mole comes out to 1.9995, which is basically 2. And this number represents N. N is the number that we use to multiply the empirical formula by to obtain our molecular formula. So let's do that now. Two times 3 is 6. 2 times 7 is 14. 2 times 2 is 4. And 2 times 1 is 2. C6H14N4O2 is our molecular formula. And these are two examples of combustion analysis calculations.